Assalamualaikum, my name is Muhammad AZAM bin ISMAIL. My matric number is 2010900977, and today I would like to present about the comprehensive analysis of power system protection, challenge, technology and emerging trend. First part is the introduction, which is power system protection is a critical aspect of electrical engineering, focused on safeguard electrical power system from fault and abnormal condition. Here are the main objectives of power system protection. The first one is reliability, ensure the protection system operates correctly during fault. Second one is selectivity, which is isolate only the fault section without affecting the rest of the network. The third one is speed of operation, which is quickly isolate fault to prevent equipment damage and ensure safety. The fourth one is simplicity and economy, which is design should be simple and cost effective. And the last one is sensitivity, which is detect even minor fault or abnormal condition early. Next, which is I would like to present about types of power system fault and cost. The first one is open circuit fault, which is break in the continuity of electrical circuit, interrupting current flow. The type of open circuit fault is single conductor open fault and two conductor open fault. Then the last one is three conductor open fault. The consequence is unbalanced voltage and current, potential equipment damage due to over voltage. The next fault is single line to ground fault, which is one phase conductor contact the ground. The cause is insulation failure, physical damage and lightning strike. The consequence for this fault is significant current flow through the ground, equipment damage and voltage imbalance. Next, which is the double line to ground fault, which is two-phase conductor contact each other and the ground. The causes of this fault is severe environmental condition, equipment failure and major mechanical impact. Then the consequence for this fault is the extensive equipment damage, safety hazard and significant system disruption. Next, which is the three-phase fault, line to line and line to line to line to ground, which is all three phase involve either line to line to line or line to line to line to ground. Causes is severe environmental condition, equipment failure and major mechanical impact. The consequence for this fault is large fault current, substantial equipment damage and significant system interruption.
Assalamualaikum and hello. My name is MOHAMAD bin SHAHAR, matrix number 2010911067. I will present about the components of power system protection and the challenges in power system protection. Okay, firstly, for the components of power system protection, a protection system has three fundamental components. Number one, instrument transformers. Number two, relays. Number three, circuit breakers. Okay, for instrument transformers, two primary types of instrument transformers, that is voltage transformers and current transformers. Okay, instrument transformers, voltage transformers. VT works on the principle of electromagnetic induction similar to CT. It has primary winding connected to the high voltage circuit and a secondary winding that produce a proportionally lower voltage. The ratio of the number of turns in the primary winding to the secondary winding determines the voltage scaling factor. For current transformers, CT operates on the principle of electromagnetic induction. It consists of primary winding, though which the high current flows, and a secondary winding which produce a proportional lower current. The ratio of primary to secondary winding turns determine the scaling factor, allowing for accurate current measurements and monitoring. Okay, second, relays. Okay, relays. CT provides the necessary input to protective relays, which detect faults like overcurrent, short circuits and ground faults. The relays then initiate the isolation of the faulty section. PT provides a voltage input to the protection relays for detecting overvoltage, undervoltage, and frequency-related issues. The relays can then take appropriate action to mitigate faults. All that a relay is an electric switch that operates on its own. Protective relays are used in electrical protection system to sense or detect fault condition and trigger a trip of the damaged circuit. Okay, and thirdly, circuit breakers. Circuit breaker is a type of switching mechanism used to regulate and protect an electrical power supply. It can be controlled manually or automatically. A fixed contact and moving contact are its two primary contacts. Normally, the connections are closed, allowing current to pass through the system. A mechanism that releases accumulated potential energy separates the contacts in the event of failure, such as an overload or short circuit. This device may be magnetic, hydraulic, or spring operated. Because it has the ability to automatically stop abnormal current flow, circuit breakers are an essential part of power system protection because they can stop malfunctions and equipment damage. This is the figure for the circuit breakers. Okay, next, for challenges in power system protection. First, coordination issues. The complexity of modern power systems of today are complex, with many moving parts and a wide range of working environments. It can be difficult to design protection strategies that take into account every eventuality. Protection coordination is the process of building and setting up protection devices, including circuit breakers and relays, to allow for the quick and targeted separation of malfunctioning power system components. The main goal is to make sure that the system is only disconnected in the impacted area, leaving the remainder of the grid operational. Okay, secondly, false tripping. Nuisance tripping, the unwarranted tripping of a circuit breakers in the absence of a malfunction, is referred to as a sympathetic tripping. Power continuity suffers from this kind of unwelcome tripping. Undervoltage from overloading, inrush current from motors and transformers, and carelessly placed circuit breakers are some of the reasons why nuisance breakers trips. Due to cascaded tripping, false tripping can result in power outage or blackouts, which can seriously disrupt the supply firms' financial operation and have an impact on power system performance. Okay, thirdly, evolving grid structures. More operational and control problems arise when renewable energy sources become more and more integrated into distribution power networks. The location and size of DERs have a major influence on how well networks are protected. Bidirectional fault current flow caused by a large-scale penetration can lead to the failure of current unidirectionally planned protection coordination mechanism. To ensure dependable protection in both grid-connected and islanding network operation modes, new protection strategies are needed. Okay, for real-world case studies, coordination issues. Case studies: Turkish transmission system. A frequency simulation model was developed to address coordination issues in the Turkish transmission system. The model considered frequency dynamics and power flow distributions, incorporating protection devices and supervisory control schemes. The study demonstrated the importance of improving frequency regulation to prevent cascading outages and blackouts. Two indices were proposed to evaluate power system robustness, helping to identify critical lines prone to overload and cascading failures. Real-world case study for false tripping. Case study: false tripping in distribution networks. A study on false tripping in distribution networks with high DER penetration highlighted the challenges of integrating renewable energy sources. The study proposed adaptive protection schemes and communication-based algorithms to improve protection, coordination, and reduce false tripping incidents. These solutions were validated through simulations on modified IEEE test feeders. Okay, for evolving grid structures, case study: microgrid protection. Microgrid presents unique protection challenges due to their ability to operate in both grid-connected and islanded modes. A comprehensive review of microgrid protection schemes discuss various methods, including adaptive protection, wide area protection, and the use of pressure measurement units, or PMUs. The study emphasized the needs for advanced protection algorithms to handle the dynamic nature of microgrids. Okay, that is all for me. Components in power system protection. and challenges in power system protection. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is IMRAN and my matric number is 201019057. So I'm gonna talk about the technologies in power system protection. So there is 5. So the first one is the protective relay. They monitor the electrical system and quickly detect fault, triggering circuit breaker to isolate the problem area. The second one is the circuit breaker. The function is switching device that physically disconnect faulty section of the power system when triggered by protective relay. And the third one is the surge protection. It safeguards the power system and its component from voltage spike and traction that can cause damage. And the fourth one is phasor measurement units, or we call it PMUs, provide the highly accurate time synchronized measurement of voltage, current and frequency across the power system. And lastly, integrated the communication. So when we improve the communication network, integrate the various protection component, enabling real-time data sharing and coordinated system-wide protection.
Hi, my name is ALIF bin MOHAMAD SUKRI. My matrix number 2010982. Let's talk about case study or practical application for power system protection. For electrical network to operate dependably and safely, power system protection is essential. This case study emphasizes the application of sophisticated protection methods to reduce operational risk and improve system reliability. It centers on a sizable urban distribution network in a metropolitan area. This distribution network provides services to a wide range of clients in the commercial, industrial, and residential domains. It is supplied with electricity via many substations that are linked to a local transmission network. Short circuit, over voltage, and equipment failures are just a few of the defects that can affect the network and cause extensive harm if they are not fixed right one. Fault detection and localization constitute the challenges portion of this case study. There are many obstacles to overcome in order to locate problems in a large network quickly and accurately. Then, protection device coordination, ensuring that protection devices such as surge arresters, circuit breakers, and relay coordinate properly to isolate failures without needlessly disconnecting network segments that are in good health. Integration of renewable energy source follows that. Coordinating the grid's adaptation to the new dynamics and variability brought forth by integration of renewable energy sources like wind and solar, which call for flexible protective measures. Next up, cybersecurity. Safeguarding communication network used for data transmission and relay coordination from cyber attack and maintaining their integrity. For applied solution, sophisticated relay protection, installation of cutting-edge numerical relays with multifunctional capabilities such as synchronization control, distance protection, and fault detection. Next, system for locating faults. By integrating traveling wave-based technologies into fault location detection system, outage restoration duration can be shortened by precisely locating fault location. Wide Area Monitoring System (WAMS) came next. WAMS implementation enable early disruption detection and adaptive protection response by providing real-time network condition monitoring. Finally, cyber security precaution. Strong cyber security policies and firewalls should be put in place to protect communication network and protection relay from hacker, assault, and unauthorized access. Increased reliability is one of the protective power system accomplishments. For instance, shorter outage and fewer of them overall as a result of improved fault identification, and quick separation capabilities. Then, improved grid stability follows. It is better protection device coordination that leads to increase the grid stability during disruption. Next, financial saving. Saving on operational costs as a result of improved problem management and less equipment damage. Finally, the ability to integrate renewables. The reliable and stable operation of the grid is ensured by the effective fusion of renewable energy source with adaptive protection technique. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is IZZAT bin AKIB 21109013. Today I want to present about the conclusion and future direction for the power system protection. As we know, the main objective of the power system protection are crucial for ensuring the safe, reliable and efficient operation of electrical power system. We also know the primary function of the power system protection is to detect fault and isolate the fault section from the rest of the electrical network. By prioritizing the objective, the power system play a vital role in maintaining the stability and continuity of power supply, preventing equipment damage and minimizing the risk of widespread outage. Okay, next is the future direction for the power system protection. Firstly is integrate protection and control system. The coverage of protection, control and automation system can lead to more coordinate and optimized power system operation, allow the better fault detection, isolation and restoration. Next is intelligent protection scheme. That is integration of artificial intelligence, machine learning and data analysis into protection system can be able more adaptive, predictive and self-healing capability, improving the overall reliability and resilience of the power grid. That's all from my part. Thank you.